I already share my slides.
No, let me just introduce you. So Giulia Cencetti is a postdoc at Fondazione Bruno Kessler. She got her PhD at University of Florence, and she has an interdisciplinary background and has been working on complex systems and complex networks. In particular, she has contributed to the emerging branch of higher order networks, and in 2021 she received the Emerging Research Award from the Complex System Society. So please, Giulia, go on with your talk.
Okay, thank you. Thank you for the introduction.
Okay, we see the slide.
Okay, perfect. So today I'm going to present a work to generate realistic temporal networks, which are synthetic networks, but which mimic real temporal networks. This work is the result of a collaboration between the Fondazione Bruno Kessler, the University of Trento, and the Technical University of Denmark. So let me start from the definition of the very basic definition of networks. A network is a structure that involves a set of nodes which are connected by links. And when two nodes are connected, we call them neighbors. So when I will talk about neighborhood of a specific node, I will mean the set of nodes that are connected to it. Now, networks are very simple structures, and they are very useful to describe many real-world systems. So, for instance, biological interactions, urban street networks, artificial infrastructures in general, and social networks. So, one of the most important problems in network science is to understand the network topology, which is not difficult when we have a simple network like this, but real networks are more like this. And in this case, it becomes very, very difficult to understand which are which is the structure of this topology. So network science often tries to grasp the most important characteristics of a specific network, characteristics which can influence the processes that can take place on it, but also which can represent the signature of some real-world features. So for this goal, many measures have been defined such that we can describe and quantify many aspects of a network topology. And I will show some of these measures later. Moreover, in many cases, networks can change in time. If, for instance, links represent social interactions, we also have that these links change quite fast in time. Okay, so when a topology of a network changes in time, we talk about a temporal network. So for simplicity, in temporal networks, we consider time as discrete, and so at each time step, we have a different static network, and the set of all these, the ordered set of all these steps makes our temporal network. Now, if we want to analyze a temporal network, we have two different dimensions to explore. One is it takes into account the topology of each specific temporal layer, which as I was saying before, can be measured, can be characterized by means of multiple measures. But we also have the temporal dimension. The temporal dimension implies following the behavior of a particular node in time and observing how its interactions change and how, if there are, and how strong are temporal correlations. However, the interplay between these two dimensions, let me call them now time and space, but with space, I mean the topology of each layer. So the interplay between these two dimensions makes the inspection a much more difficult problem if we want to take everything into account. For this reason, in this talk, I will propose a simplification strategy which corresponds to decompose the temporal network in its small building blocks. So these building blocks include both spatial and temporal dimensions, but small. So in other words, we assume an egocentric perspective, or a perspective which is centered on a specific node, and we will do it for each node of the network. And for this node, we only consider its neighborhood, by also disregarding all the interactions that can occur between neighbors. And we consider this neighborhood just for a few time steps. So the number of time steps is a free parameter for our model, but in the following, I will consider it fixed at 3 time steps. So this structure that we find, we call it an egocentric temporal neighborhood. During these time steps, we also pay attention to keep track of all the preserved interactions. So for instance, here you see that the ego node is interacting with node A at the first time step, then this interaction continues until the second time step, and then it ends. So we store the shape of the interactions, but we do not consider the identity of these nodes, the identity of the neighbors of the ego node. So we only are interested in the shape of the interaction, okay? We do not store the identity nor any characteristics of the neighbors. And so this concept is so simple that we can encode each interaction of this ego node into a binary string. And so the entire egocentric temporal neighborhood can be univocally described by a binary signature. This is possible only because we are neglecting all the interactions between neighbors. So we are simplifying the problem, but this helps a lot for the algorithm velocity, and which makes possible also to analyze very big temporal networks. Now, these egocentric temporal neighborhoods can be extracted for each node of a network and at each time step by using a sliding window over time. And so let's suppose that we do it for a real network and we store all of them together. Then we found a way to decompose a temporal network in its building blocks. Now, how can we use them? Well, we can generate a new network. Why? Well, first of all, it will be a test to understand if these building blocks that we choose really contain some fundamental information about the network. And in this case, the new network will be similar to the original one. Then, because if it works, the new network will preserve many of the characteristics of the original graph, and it could hence represent a suitable replacement to it. A replacement is, for instance, useful when we deal with social data and we do not want to share sensible information about individuals. But in general, synthetic networks can be useful for many applications, and for instance, also for data augmentation, or in general for the possibility to have a more complete data set when in situations where it is only possible to collect an incomplete one. But I will come back to the applications later. Now let's try to understand how we can use these building blocks to generate the new network. So first of all, we need to extract from the original graph all these egocentric temporal neighborhoods, and we store them as with these binary signatures. Then the new network will be generated node by node and step by step. So we first need a tool that, given the neighborhood of an ego node in 2 time steps, tells us how to prolong it and to obtain the third step. Okay, and this tool is a dictionary, which is a structure that classifies all the neighborhoods that we found in the original network according to the first 2 time steps. And for each of these key, it stores all the possible third time steps with also their frequency of appearance. So at the end, for each key, so for each neighborhood of length 2, we have a probability distribution on all its possible prolongations. Then, now let's suppose that we already generated the first 2 time steps of our new network, of our synthetic network. And then I now explain how to go on and generate the third time step. And then I will come back to explain how to initialize the system, so how to generate the first 2 layers. So now let's suppose we have these 2 layers. We consider one node, and for this node we extract from this network, this temporal network, its egocentric temporal neighborhood. Then we look into the dictionary for this structure, and we sample from the associated probability distribution a possible third step for this neighborhood. Then notice that this third step can involve some of the nodes that were also present in the first 2 steps, but it can also involve new nodes that the egocentric, the ego node would like to connect to. So we do not know at this stage which this new node will be, and so we just describe it with a question mark here in this scheme. And so this link that we add is a stub or an open link. Okay, so we know that there is a link that will be connected to some other nodes, but at the moment we do not know which node will be there. Okay, so now that we have extracted this structure, we put it into the third layer of our temporal network, and we insert it in, as directed links. So each connection is represented by a directed link, which goes from the ego node to the node, the other nodes that the ego node would like to be connected to. So each directed link represents a request of a connection. Then we can do this for all the nodes of our network, and so we obtain a provisional third layer, which is directed. Now, in order to make it definitive, we need to validate or not these connections. Now, since we have a directed network, only half of the links should be validated, because the directed links are twice the number of non-directed ones, because if you have node I and J, you can have a directed link from I to J and a directed link from J to I, while when we have only undirected links, we only can have one link between them. Okay, so first of all, we validate all the bidirectional links, those which represent reciprocal requests. Then for the unidirectional, we validate half of them by choosing at random. And then in the last step, we connect the stubs. So the open link, we connect pairwise the open links, and again randomly. Okay. So at the end, we have obtained the third layer of our temporal network. Then we can go on and generate the fourth, the fifth layer, and so on, as many times as we need to generate our new network. Then let me take a step back to explain how we can initialize the system and generate the first two layers. So the first layer is generated using the configurational model, which is a model for generating static networks with a given degree distribution. The degree is the number of connections of each node. And so we choose the degree distribution of the first layer of our original network in order to build the first layer of our new network. Then the second layer is built actually using our the method that I explained, so based on egocentric temporal neighborhood, but just rescaled in time. So instead of having a dictionary where the entries have 2 time steps, now we use a dictionary where the entries only have 1 time step, but we repeat the same procedure. Okay, so we generate the second layer like this, then we have the third layer, and so on. Okay, so now that we understood, I hope, the procedure to generate this new network, let's see some results. So here I am reporting for some different temporal data sets, which are all social interactions, physical and remote. I am reporting the number of interactions in time that we find in the original data set, which is represented by the black curves, and in the generated network that we generated using our procedure, which are represented in orange. So here you can see that there is a similarity between the two. We are also able to reproduce the temporal periodicity that we find in social data sets, which are due to the day, night, and weekdays and weekends periodicity. And to do so, we use multiple dictionaries. So instead of having a unique dictionary for the entire data set, we use different dictionaries for different days of the week or for different hours of the day. It depends on the data set. Yeah, okay. So from this, we can see that the two plots, the orange and black, are quite similar for all the examples, but how similar they are. In order to answer to this question, we introduce some competitors. So we consider 3 other different models to generate temporal networks, which mimic an original one. 2 of them are based on temporal motifs, so essentially temporal small structures that are repeated in the network, and one is based on deep learning. And here is the result that we find by using also the competitors for 3 different data sets of physical interactions, a hospital, a workplace, and a high school. And as you can see, again, the black curves represent the original network. The orange curves represent the networks obtained with our method, and the bluish are the competitors. As you can see, our method, the networks generated with our methods are most similar to the original ones than with respect to the competitors. Also notice that for one of the competitors, the interactions were so high that we had to plot them into separated insets. But now I want to show this comparison also for what concern other measures, other topological measures that we can define on temporal networks. So here I am reporting the distance between the original network and the generated ones for what concern each measure that you see on the left, and for the same 3 different data sets. This distance is computed using the Kolmogorov-Smirnov test, which is a way to compare distributions. So shorter bars mean a short distance, so more similar networks. And you can observe that the orange bars are usually the shortest ones. And for the measure of density, which is the number of links at each time step with respect to the number of nodes divided by the number of nodes. For this measure, I also show you the actual distributions. And so again, from here, you can see that the distribution that we obtain with our method is quite similar to the original one. Then, before concluding, I just want to show an application of this method. So I was mentioning before the data augmentation. Well, it is sometimes useful to have long data sets, so long temporal networks, in order to have to simulate some specific problems. Think, for instance, about a simulation of a spreading event. And if we have only a short data set, we are not able to see the long-term effects of this event. So as I was explaining before, in our method, when we generate the new network, we do it step by step. And so we can repeat the procedure how many times we want. So we can generate a network which is long as we want. And so, for instance, here we did an experiment. So this is a data set of a workplace which is 2 weeks long, but we cut it by assuming that we only had access to the first week of interactions. So from this first week, we can generate our dictionary and then generate the new network. And what we obtain is this. And if we compare it with the original one, we see that they are quite similar. Then another application is the size expansion, which involves the expanding the number of nodes in our network. Again, think about a simulation of a spreading event. If we have a very small population, it is impossible to see which is the real effect of spreading. So we need sometimes large populations. And with our model, it is possible to enlarge the population, because again, the number of nodes in our network is just a parameter that we set at the beginning of the generation of the generating model. So this is another experiment that we did. We took the high school data set, and we assumed that we only have access to half of the nodes. So from this half of the nodes, and we generated our dictionary and our temporal network with the correct number of nodes, and then we can compare it with the original one, and we see that we find again a similar structure. And then we can also do both, of course. So we assume that we have a shorter and smaller data set, and we are able to reconstruct a similar a temporal network which is similar to the complete data set. So in conclusion, we are able to generate a temporal network which is similar to the original one, just using as information the decomposition of the original network in egocentric temporal neighborhoods. In my presentation, I only showed examples of social interaction datasets, but I wanted to say that the method is general and it can be applied to any temporal network. And so thank you for the attention, and I also want to thank my collaborators for this project.
Thank you. Thank you very much for the talk. Questions or comments? Yes, please, Maxime.
Hello, Giulia. Thanks. Very nice talk and very nice work.
Hi, Maxime.
I think I missed it. I was curious. So when you decompose it, you build the ego network for every node in the network, I guess?
Yeah, exactly.
Okay. And do you know if it can work if you do it only for a few of them? Or maybe if you pick them right, or...
Well, if you only use some of them, it is similar to the situation that I was that I was explaining now at the end. The situation where we only have access to part of the original networks, and so only part of the nodes. And so we are able to reconstruct a network which is similar to the original one, but of course it is more, it is less precise because we have less statistic to work on.
Okay, thanks.
Yeah, but it is possible in general. Thank you.
Yeah, thanks.
Any other question or comment? I have one question concerning the comparison that you did with the competitors. In the slide, I mean, you said, I mean, in your model, you typically tune, in a sense, you do your search for the structure, for the dictionary at given days. So are also the other system doing something similar? Because I saw that in some cases, I mean, there was a dynamics that was essentially stationary.
Yeah, it is a good question. So I can show again the slide. So
yes,
it's better. Okay. Okay, so there is one of the model, the one that is reported in the insets, the one with huge interactions, that is based on deep learning, and it is able to reconstruct the periodicity. The other models are not able to do that, but just because it is not a feature that is inserted into their model. But I want you to notice that if we didn't use this strategy of multiple dictionaries, so we would, if we construct the new network by using a unique dictionary, what we would obtain would be something flat. Of course, we wouldn't be able to see the periodicity, but the height at which our flat distribution will be, it will be on the average of the number of interactions. While if you see the competitors are usually lower than the average and sometimes higher. So the point is that, of course, this strategy of multiple dictionaries is a plus that we inserted in our model in order to reconstruct this. But even if we didn't have it, we would be able to reconstruct the correct number of correct average number of interactions.
Okay, thank you. There is, I think, another question, Enrico.
Okay.
Yes. Hi, Giulia. Thank you for your presentation.
Thank you.
I don't know if you don't see me very well. Okay. The question is, in this presentation, you always have networks made up of homogeneous nodes. I mean that the nodes cannot be distinguished. There are no different kinds of nodes. For example, we know that spreading processes may be related to some node properties like ages, for example. So did you try to reconstruct a different ego-temporal neighborhood for different kind of nodes?
Yeah, thank you. It's a very interesting question. We are actually working now, not working, but thinking about possible improvements of this method, because actually with this very simple model, we are also considering that every node is statistically the same. They can have the same role in our network statistically, but it will be interesting to differentiate between nodes. So use more their characteristics, like their degree, but also some other metadata. It will be possible. We are working on this. So yeah, I hope that soon there will be another model 2.0.
Thank you.
Thank you.
Other question or comment? So if not, I think we can close today's session. Let's thank again Giuseppe and Giulia, and thanks to all of you to participate, to listen to the seminar. Next session will be May the 12th, and probably it will be the last for this season. So thank you very much, and bye-bye to all of you.
Thank you. Bye.
Thank you.